Hello students, this video is showing some example problems that correspond to your classwork from March 23rd. I have different tabs set up for the three examples I'm going to be doing, so I'll do something from number 7 first, then number 15, and then number 16. So let me start with number 7. Number 7 is graphing logs. I'll do my first example of graphing just log of x. We have this relationship where we can change a logarithm into an exponential. So the exponential version of this would be 10 to the y power equals x. When there's no base written, then it's inferred that that's base 10. Because these are inverse functions, the way that we would have seen this before we went on break would be x and y being interchanged. So we would have had 10 to the x power equals y. And we talked about the exponential graphs in the past. We said that all of them would pass through the point of 0, 1. And they had an asymptote of, in this case, the x-axis. So when we look at a logarithm graph, the x and y's are going to be changed. So this graph here, I'll make it green, is going to be passing through the point 1, 0. I have the x and the y interchanged. And the asymptote is going to be at the y-axis, or the line x equals 0. If we were to plug into our calculator the log of 1, we should get the output value of 0. So take a second and just check that on your calculator. What that's saying is that 10 to the 0 power equals 1. These are equivalent statements. This one in exponential form and this one in log form. We can use this as our base graph to maybe graph something different. Let's instead graph log base 5 of x plus 8. The base isn't going to change the graph too much. We're just going to look at this in terms of a graph transformation. And we know that because we have 8 inside the parentheses, that the whole graph is going to shift to the left by 8 units. So that point that I originally had, which was at 1, 0, is going to shift over to the left by 8 units. So it would have started here at 1, 0. 1, 2, 3, 4, 5, 6, 7. And it's going to be at -7, 0 is our intersection point. And then our asymptote, instead of being at 0, is going to be at x equals -8. And then I'll draw my graph through this point, growing slowly. Now, how could we find this point here? How could we find the y-intercept? Well, we know that the y-intercept shows up when the 0 is plugged in for x. So in this particular graph, if we looked at log base 5 of 8, that would give us some decimal equivalent. I'll plug that into the calculator. Log base 5 of 8. And I'm getting about 1.3. So this graph should probably be a little bit lower, right? Let's erase this. Let's redraw my axis here. And it's probably going to be more down here. Right? For my third example, I'll do log base 7. And this time we'll put a plus 10 outside the parentheses. When we've got something outside the parentheses, we know that that's going to shift the entire graph up by 10 units. So in this case, the point that was at 1, 0 is going to go up to 10, 0. Or, no, 1, 10. And our asymptote hasn't changed because we're not moving left or right at all. So we're just going to have our graph drawn like this. The next set of examples will be for question number 15. The lecture that we'll be looking at for Wednesday involves solving exponential and logarithm equations. And so we'll need the ability to expand and compress logarithms for the solving of equations. And so that's what these problems are really meant to set us up for. So let's look at log base 2 of 6 times x. And I want to expand this using the laws of the product rule, the quotient rule, and the power rule. When two items are multiplied together inside the parentheses, we actually call this the argument, what we're taking the logarithm of. When two items are multiplied together, we can split this into two separate logs. The base always stays the same, and I'll put an addition symbol in the middle, and then the two arguments are split, 6 for one and x for the other. Looking at a different example, let's look at log base 5 of x cubed times y to the 6th power. This is going to involve sort of a two-step process. We use the same idea we just did in the last one. I'll split this into two separate logs, breaking up the product. But then I'll use the power rule, which lets me take any exponent and bring it down into the front. So log base 5 of x, and the 3 comes down to the front. And here, log base 5 of y, and the 6 comes down into the front. This will be particularly useful when we're solving equations that have to do with finding the amount of time that it takes to invest and make a certain amount of money. And then I'll do a third example. I'll use natural log for this one. And I've got a quotient rule. So the top is going to get split up as a product the way we did in the first two. But the bottom, anytime you have something that's divided, that becomes subtracted. The first two logs we can leave alone, but I want to make some modifications to this. I want to instead write this as the natural log of c to the 1/3 power, so that I can bring that power down into the front. So I'll have natural log of A plus natural log of B minus 1/3 natural log of C. Okay. For number 16, I'm going in the opposite direction. So I'm taking logs that are expanded and putting them into a single log. So in this case, we're going to combine a couple logs together. We saw in the previous example that a number that's in the front acted as an exponent. So I can bring that 3 up as an exponent on the x. And similarly, the 1/2 can move up as an exponent. And it's going to be outside the entire argument. We know that 1/2 is the same as square root. So I'll just rewrite this as square root x plus 1. And now I've got two different arguments that would need to be multiplied together. So my final answer is going to be x cubed times the square root of x plus 1. You don't have to put the parentheses around it, but sometimes we'll put parentheses around it just to denote that that's the entire thing that we're taking a log of. For the next example, let's combine, 3 natural log of s plus 1/2 natural log of t minus 4 natural log of t squared plus 1. Let me just check my time. I've got 3 minutes. I can only make 15-minute videos. So the 3 will be an exponent, s cubed. The 1/2 will be a square root. And then the 4 will come up as an exponent. The two items that are multiplied stay in the numerator of a fraction. But then, actually, let me get rid of these. The item that's subtracted will go down into the denominator. And I'll just put parentheses around the whole thing, like this. So that's your final answer. All right, if you have questions, send me an email, and otherwise, hopefully I'll see you in Zoom tomorrow. Bring your questions to office hours. Have a great day.